Good afternoon. I hope you had a good lunch, so you can sleep well now. My name is Ladislav, and my talk is going to be about something that has been almost forgotten, but it's still to be counted on when you maintain a system for an automated sample processing. I am a senior malware researcher at GEN, and I have been part of the AV industry for 18 years already. And whilst my CV includes 5 companies, it has still been the same chair. We've been renamed and acquired and renamed again. I did reverse engineering, I did malware analysis, I built internal tools, cleaning tools for file infectors. I did a Windows emulation engine and ransomware decryptors and many YARA rules to detect those file infectors and ransomware. What this talk is going to be about? I'm going to talk about file infectors, which are the true computer viruses, and I'm going to present the prevalent strains that we see in our user base. I will show you their brief description and will delve into quirks of detection of file infectors with YARA. Okay. Come on. Yeah. General public and some journalists, they still tend to use the term computer virus for every malware, malicious program that are out there. Although not correct, it comes from the term that started to be popular like 30 years ago, so don't. This is not a virus, this is a malware. The true viruses mimic the behavior of biological viruses, and they are defined as programs that when executed, then they replicate by inserting their own copies into the healthy other programs. Even though blog posts don't mention them too often, they still exist. And I can divide them into 2 categories. First of them are so-called prependers. Those replace the whole exe with their own body. And the original exe is appended to the end. Sometimes it is also inserted into resources, or exceptionally can be even in special separate files. Those are very easy to write. You can make them as a Python script. They are very easy to detect. They are very easy to clean. Some of the strains we saw lately include the Black Moon, Blastic, Fantastic, Lamer, which shows how sophisticated this virus is. Memory, the last one that seems like a typo. Well, it actually is, but not on my side. We named it after a string in the virus body. The second group is so-called appenders. Those are more sophisticated. The virus body is incorporated into the exe, usually to the end, and the code execution is altered. So most often the virus code runs first, and then the run is transferred to the original code of the program. Very often those are polymorphic, so every copy is different than the previous copy. They are often encrypted. Those are quite hard to detect by static detections. As an example, I could present Solidity, Virut, or Expiro. How do they achieve this code execution altering? Well, there are several ways how to do that. First of them is to modify the field that's called address of entry point in the PE header. You know, this is a typical structure of a PE file, and then in the header there is a field that's called address of entry point. In the infected copy, which is usually slightly bigger because there is a virus code at the end, all you need to do is to modify the address of entry point so it goes to the end first, and then, if necessary, then it will transfer back to the original code. The second way how to achieve the same functionality is to modify the code at the entry point itself. So in the healthy copy, in the original copy of the program, again, there is this address of entry point pointing to some code. In the infected copy, there is the same value, but if you look at the code, it is different. That is the second one. And the third one, you can also modify some random instruction in the code section of the program. So again, in the original file, you see the entry point looking like this, and the infected one, you see the same code. But if you diff those sections, you will see that in the healthy file, there is some instruction, and in the infected file, there is a different one. So, what is spreading? What do we see in our user base? This is, here is the most prevalent strains of file infectors that we see in our user base, including their aliases. Floxiv, Sality, Virut, Expiro, Neshta, Ranaus. The last one, again, that looks like a typo, and it is, but not on my side, because it creates a file in system32 directory which is called runaus.exe. It is quite many of them that we see. This is the numbers of protected users per month in fourth quarter of 2023. So it's not like 15 years old or something. It's still up to date. It's still actual. If you look at the countries, it's mostly Africa or Near East. The scale shows so-called risk ratio, which is the term we use as a number of attacked users divided by the number of active users in that country. So let me show you a few of those strains, how they operate, how they infect files. Floxiv is the appender kind of file infector. The code at entry point is rewritten, so you can see that it's on the same address, but the code is different. There is a small loader in the code sections, and the most of the virus body is placed in the PE overlay. The second one, Sality, it goes by modifying the address of entry point in the header. So the original code and the entry point of the virus has its own different address, and also obviously is different. It's very polymorphic, it's encrypted. And the virus body is appended to the last section, which is enlarged in order to hold it all. One of the most problematic, at least from my personal point of view, is Virut, that has a highly polymorphic stub. The first thing what it does is that it's called get tick count repeatedly, and tries to find virtual machines by speed, how fast it can call this API. It injects processes. If you look at the machine that is infected by Virut, that some functions of interest are changed, that are hooked, for example, anti-open file. For those who saw an API like this ever, and it should rather look like this. However, there is a call that it should not be there. It also modifies the host file. So for the local host, there is some Chinese domain, and it also modifies HTML files. So there is an iframe which points to the same domain. Expiro. This one is interesting because it is capable of infecting both 32-bit and 64-bit exes. It is quite large. It is more than 240 kilobytes. The entry point code is rewritten by the virus stub and is typical by having multiple push instructions at the beginning. Black Moon is one of those that are more recent. It's like from 2018, and it is a combination of a file infector and a Monero miner. If you execute a sample, then it will infect all files on the hard drive, and then it will also modify HTML files on the hard drive, and finally it will drop and execute the Monero miner, 32-bit or 64-bit, depending on the architecture. The file infector part is not really sophisticatedly written, and it doesn't really care about reinfection. So if you list and the file overlay, you can find multiple PE files in it, and all of those are like steps of the infection. It also doesn't really care about reinfection of those HTML files, so it is very common. You see several executions of the monorominer in one HTML files. Now, why am I even talking about it? I said that it's quite old stuff, they're all dead and so on. Why is this still important? Why am I even talking about it? Well, if you get an infected file, then everything important is at the end of the file. Static features that you use to detect or cluster or use for machine learning, they don't matter anymore. So all of this, like strings, resources, PDB path, icon hash, whatever is in the exe doesn't matter anymore. So if you have a machine learning or a clustering system, could be like a group of logbit samples, could be a group of notepad exes, could be a group of samples that create an interesting mutex, all of them may be tainted by file infectors. So you need to do some pre-processing which tells you, hey, is there a file infector or not? If not, then we go back to the original clustering. If yes, we need to process that file infector. Also, by their nature, file infectors produce large amount of samples. It's not a problem to get 1,000 of samples from one single PC or a sandbox. So if your sandbox uses to resubmit dropped files, it goes haywire pretty fast. So at Gen, we use a YARA pre-processing to check whether they are infected by a file infector, and I'm gonna tell you how we do that. As you probably know, the YARA is sometimes called a pattern matching Swiss knife, and it can detect both static features. For example, this simple rule that everyone, even if you don't know YARA, you can pretty much see how it works. So if you run the YARA scanner on an HTML file from this conference, you will get a detection. But they can also detect a behavioral feature. So again, you find a simple YARA rule, behavioral, that detect overwriting the exe files. And if you run it with a behavioral report, you get a detection. In general, YARA has quite a tradition at Gen. Formerly at Avast, we are even present as one of authors. If you list the appropriate document, you will see Avast being there as one of the authors. We also have very high standards for our internal YARA rules. We have very low tolerance for false positives. We want our YARA rules to be perfect or almost perfect, and trying to minimize the false negatives. And this is not possible to do with the official upstream YARA, so we have our own. To be able to deal with the file infectors, we did many improvements to the file infectors and also pushed them into the upstream YARA, like this one. So we enhanced the PE module, that is very important when detecting anything related to file infectors. So we added quite a lot of fields that are supported, and we also added a lot of constant. And that's not the only thing that we enhanced. We also enhanced the behavior module, the cuckoo module, because originally, for example, for files, there was just a function that checks for file access, but it wasn't enough for us. We obviously kept the old function as it is, but we also added the function detecting file read, file write, and file delete. The same we did with the registry functions. Originally, they only was the key access, but again, we did the same. So we can now detect key read, we can detect key write and key delete. Also, the functions themselves were enhanced. So instead of them simply returning Boolean, so it the upstream YARA will tell you whether that happened or not. We changed that, and now we use that it returns an integer, which means that how many occurrences of that action happened in the sample run in the sandbox. Because this is about the community, we also want to give to the community, and we always try to push our changes to official YARA. Not every time it gets accepted. So if you join our effort and say you would like to see those changes in the official YARA, join us, because I think that the more people will want a feature, then the more likely the feature gets through. So how do we do that? How do we detect file infectors with YARA? It could be easy, or it could be very challenging. Like I said, prependers, those replace the body of the file with their own body. So if you want to detect a prepender, it is very easy. You know, all copies are the same. So you can even make a hash of a first like 400 kilobytes and it will work. On the other hand, appenders may be easy if the file infector is not polymorphic, like Ranaus or Neshta. But it's very hard on viruses that are polymorphic, like Sality or Virut. The good news is that most of the file infectors are no longer developed. Why is that a good thing? Well, once you cover them, you're good. And you can forget everything and it will just work. We did some cleaning tools at AVG and Avast. They are more than 10 years old, but they still work up to today. So again, once you cover them, you're good. It is also very easy to write a generic rules that detect not a particular infector, but all of them. This is an example. If you have something that writes to large amount of exes, maybe the zero here could be larger, like 100 or at least 50, but still you get the idea. It's not that hard. So, prependers. All samples have the same primary exe, and the original one is in the overlay or in the resources. So, those are usually very lamely written. Sometimes they are funny, like this one. Apparently, someone forgot to check if the sample is already infected, so it keeps reinfecting and reinfecting every run. So the samples grow bigger and bigger. Static detection is very simple. If you have a non-packed sample, any string will do. This is an example of Neshta infector. No comment about that, but writing the YARA rule is obvious. You don't really need to be a rocket engineer to find that out. However, it is always good not to rely just on the string, but also to add some detection of a file format. Otherwise what? Well, otherwise that YARA rule would actually detect itself as well, which you don't want to. It would also detect any text file that would be small enough, like smaller than 10 kilobytes. So you want to put there something like, I want it to be a PE file, not just the string. If the sample is packed, which is also the case, sometimes the infectors are packed with UPX or Empress packer, then you can use that any byte sequence you can put into the YARA rule and it will work. Remember, they are no longer developed, so it's not like next 14 years you will get a new sample with a new sequences. So it's okay. A few tips that you can use when you write a YARA rule for file infectors is don't check for file size. It is much better to use the PE module of YARA and check for the size of image. This is because the file may be infected multiple times, and typically very often is, or the file could have a large overlay, so file size does not really work. You can also check for the size of the overlay there, using the YARA rule like this. Also, don't forget that the infected exe may be in the middle of the healthy exe, like a resource or an installer package or a part of the overlay. You probably want only to detect the primary exe having the infector, not anything that is packed in the resource, because that's the job of the unpacker or the installer itself. It is also common to have multiple copies of the same infector in one file, be it appender or prepender, and it is also common that you have more than one infector in one file. It is pretty often. For appenders, static detection is a problem because most of the traditional method when you check for strings, for code sequences, they just don't work because the virus body is often encrypted at the end. But there are still a few things that you can use. Most often the entry point goes to the last section. This is not typical when you build an exe, or typical exe has one code section and the entry point goes to there. The last section is often marked as read, write, execute. Again, this is not a typical one. Also, because they are often encrypted, that means that the last section, the virus body, has a very high entropy. How would such YARA rule look like? This might be a good example how to detect that. And because nothing on the world is easy, then this behavior is also typical for a packed sample. So you may want to exclude those packers that you see most often. There is some good news that you can use when checking for a file infector. Some of them do check their presence in the file. And how they do that? You may compare the original file with the infected one, focus on the header, and you can see some differences. Most of the time, they use fields that are not used. So in the DOS header, basically all of them except the first and the last one. The NT headers, there are timestamp. This one can be abused because basically it's not important for anything. Pointer to symbol table, number of symbols, sometimes they get modified. Also in the section header, the pointer to line numbers, I will show you an example later. So if you compare the original file with the virus, the infected one, you can see that there is a change in the timestamp. So because we added a timestamp field to YARA, so you can write a very simple YARA rule checking for the virus file infector. Again, it would be good to add some more check here to confirm. For example, you don't need to check for a format because the PE module automatically implies that it is a PE file, but I would like to see more checks here to confirm that it really is a virus. For example, the entropy of the last section would look good there. Another sample, if you look here on the image section header, you can see something that is really, really suspicious. What is that? This. That is just not the timestamp. Yeah. So again, you can enhance the previous rule with the new value, so you will catch also the new variant. However, with all due respect to static detection, it does not always work well. So you should really focus on a behavioral detection. That one will skip any polymorphism, any entry point obfuscation, and it will work generally much better than static detections. For example, like I said, file infectors often modify multiple exe files, so there is nothing more simpler just to write a YARA rule for that. And if you tune your value and exclude some known installers that do that, you can use very simple rule that will detect file infector behavior. Again, some installers do that as well, so you need to exclude them, put them into whitelist. File infectors, like any other malware, may create a special files. So if you see that someone is creating link info DLL inside the Windows directory, it's a pretty good candidate for making a behavioral-based YARA rule. In particular, this one is Alman file infector. It also applies to registry entries. So if you see something like this, then it's yet another file infector. And the most important thing, like any other malware or most of the other malware, file infectors also need to check present on the machine, like if they are already running. And they often do that by creating a named object, which could either be mutex, semaphore, event, atom, whatever, or name section. For example, Virut file infector creates a very specific mutexes or a named sections. So if you see that, again, you can make a YARA rule behavioral based, and it will detect you Virut quite reliably. And again, because nothing is as easy as it could, then there are some exceptions. As for the markers, like I say, for the static detection of the markers of infection, if the file has been cleaned by a cleaning tool, very often the marker stays there. This one is a marker of the Sality file infector. We see a lot of those. We actually had to make a special YARA rule just for these kind of samples. They are not malware, they work, even though they are not the same like original. So we had to do a special filtering of samples modified like this. Also, the legitimate installers may modify and drop many exe files. An example from my last practice was the Foxit PDF reader, whatever is that. It just installs itself without user consent. And all our YARA rules modifying, that detect modifying of exe files, they were screaming like this is an infector. So you need to put that on the exclusion list as well. There are more things to watch for. Some legitimate applications may create named object, the same like file infectors. It may have a legal reason. For example, there are immunizers. Those are programs that run in the background, and they will just create the mutex or named section just to fool a real infector and prevents it from running. Also, some AV solutions do that. Or, the most funny, is just random test programs. This is a sample that I processed like 14 days ago. That was just a sample. It does nothing else than this. Let me make it a little better looking. Yeah, this is all that it does, nothing else. But because it creates the named object that is the same like the Virut infector, now our systems were screaming that it's a false alarm. Well, it is, but I had to do that. I had to include that sample in an exclusion list. So basically that is it. So what is the conclusion of this talk? File infectors are mostly the blast from the past. However, any kind of automatic sample processing will be messed even in the present. So if you have an automated system, you need to process samples differently when you find out that they are infected by file infector. So you need to maintain an up-to-date exclusion list and check for false alarm periodically. Thank you very much. That's it from me. And if you have any questions, please file them.